Hello, dear space explorers. QUASARIA channel is back with you. Today we will embark on the most incredible journey imaginable. A journey that will encompass absolutely everything. From the smallest particles existing at the boundary of the possible to the most distant corners of the cosmos, lying beyond human imagination. Over the next hour, we will traverse a path of 61 orders of magnitude. We'll begin in a world where space and time lose meaning, where the strange laws of quantum mechanics reign. Then we'll ascend through atoms, molecules, cells to the human. We'll continue our path through our planet, the solar system, the galaxy, and reach the most distant boundaries of the observable universe. This is not just a scientific lecture. This is a journey that will change your perception of reality. After it, you will look at the world with completely different eyes. Are you ready? Then fasten your seatbelts. We're beginning our cosmic odyssey right now. Planck length, the absolute limit of existence. Our journey begins at the most extreme point of creation at the level of the Planck length. This is 1.6 times 10 superscript 3 meters. To understand the scale, this is so unimaginably small that the ratio of the Planck length to the size of an atom is approximately the same as the ratio of an atom to the entire observable universe. Stop for a second. Read this again. The Planck length is as small compared to an atom as an atom is small compared to the entire cosmos. At this scale, the very concepts of space and time begin to break down. Physicists suppose that here space-time may not be a smooth continuum as we perceive it. Instead, it may represent foaming, seething quantum foam, constantly appearing and disappearing virtual particles and microscopic black holes. This is the limit of our physical theories. Beyond this boundary, modern physics is silent. We don't know what happens there. Perhaps at this scale, the laws of quantum gravity operate, which we haven't yet discovered. Perhaps entire universes are born and die there in every instant. We simply don't know. Planck time, the moment of creation. There also exists Planck time, 5.4 times 10 seconds. This is the shortest interval of time having physical meaning. Light, the fastest thing in the universe, travels exactly 1 Planck length in Planck time. It's believed that in the first Planck moment after the Big Bang, the entire observable universe was the size of a Planck length. Everything you see around, stars, galaxies, galaxy clusters stretching for billions of light years. All of this once fit into a point smaller than a proton. Quarks and gluons, the building blocks of matter, rising to a scale of about 10 superscript 1 meters. We enter a world that could be explored using the most powerful particle accelerators. Here dwell quarks, fundamental particles of matter from which protons and neutrons are composed. Quarks never exist alone. They're always bound to each other by a force that becomes stronger when attempting to separate them, like a rubber band that stretches but doesn't break. This force is carried by particles called gluons, from the English glue. 3 quarks form a proton or neutron. 2 quarks form a meson. There are 6 types of quarks with whimsical names: up, down, strange, charm, bottom, and top. Each has its own mass, charge, and quantum properties. According to string theory, one of the most ambitious attempts to create a unified theory of everything, even quarks aren't fundamental. Instead, they may be tiny one-dimensional strings vibrating in multidimensional space. Different vibration modes of these strings manifest as different particles. An electron is a string vibrating one way, a quark another way, a photon a third way. Imagine the universe as a gigantic symphony, where each note is an elementary particle, and the entire cosmos is a grandiose musical composition performed by the strings of reality. Protons and neutrons, the atomic nucleus. At a scale of 10 superscript 1 meters, we encounter protons and neutrons, particles composing atomic nuclei. A proton is approximately 100,000 times smaller than an atom, but contains 99.97% of its mass. Inside a proton, 3 quarks rush about at incredible speed, constantly exchanging gluons. Between them flicker virtual quark-antiquark pairs, arising from the vacuum and immediately annihilating. A proton is not a static object, but a seething cauldron of quantum activity. The proton is incredibly stable. Its half-life is estimated at a minimum of 10 superscript 3 years. This is 10 trillion times greater than the age of the universe. The protons you consist of will probably outlive all stars, all galaxies, possibly even the universe itself. Atom, almost absolute emptiness. Finally, at a scale of 10 superscript 1 meters, we reach the atom, the basic unit of a chemical element. Here is where the real magic of scales begins. If you enlarge an atom to the size of a football stadium, its nucleus would be the size of a small pea in the center of the field. And the electrons? These would be specks of dust rushing somewhere in the stands, moving at speeds close to the speed of light. An atom is 99.9999999% empty space. Read this again. 9 nines after the decimal point. You, reading these words, the chair you're sitting on, the planet beneath your feet. All of this consists almost entirely of emptiness. You're mostly nothing, held together by electromagnetic forces. Why don't you fall through the chair? Why don't atoms pass through each other? It's due to the Pauli exclusion principle and electromagnetic repulsion. The electrons of the atoms in your body and the electrons of the atoms in the chair repel each other. You've never truly touched anything. Between your hand and any object, there always remains a tiny gap. You feel electromagnetic repulsion, which your brain interprets as touch. Quantum strangeness. At the atomic scale, reality behaves completely opposite to our everyday experience. Here the laws of quantum mechanics rule. The most successful and simultaneously strangest theory in the history of science. Heisenberg's uncertainty principle says that it's impossible to simultaneously know precisely both the position and momentum of a particle. The more precisely you measure one, the less definite the other becomes. This is not a limitation of our instruments. It's a fundamental property of reality. Quantum superposition means that a particle can exist in several states simultaneously until the moment of measurement. The famous thought experiment with Schrödinger's cat illustrates this strangeness. A cat in a closed box can be simultaneously alive and dead until you open the box and look. Quantum entanglement, a phenomenon that Einstein called spooky action at a distance, allows two particles to remain connected regardless of the distance between them. Measuring the state of one particle instantly affects the state of the other, even if they're at opposite ends of the universe. These effects aren't just theoretical curiosities. Modern technologies are based on them. Transistors in your computers and smartphones, lasers, MRI scanners, atomic clocks. Quantum mechanics is not just an abstract theory. It's the foundation of modern civilization. Philosophical digression, the nature of reality. Before rising to the next level of scale, let's pause for a moment of philosophical reflection. Quantum mechanics calls into question our intuitive understanding of reality. In the macro world, things exist independently of the observer. The moon is in the sky even when you're not looking at it. But in the quantum world, the act of observation affects what's observed. A particle is in a state of superposition in multiple states simultaneously until you look at it. What does this mean for the nature of reality? Does objective reality exist independently of the observer? Or does consciousness play a fundamental role in shaping actuality? Physicist John Wheeler proposed the concept of a participatory universe, the idea that observers don't just passively register reality, but actively participate in its creation. The universe, in his opinion, is not just a mechanism operating according to given laws, but a system that acquires specific properties through acts of observation. Danish physicist Niels Bohr, one of the fathers of quantum mechanics, said, "If quantum mechanics hasn't shocked you, then you haven't understood it. Molecules, the chemistry of reality, rising to a scale of several nanometers, 10 meters, we enter the realm of molecules, groups of atoms bound by chemical bonds. Here we observe the first sign of true complexity. Two hydrogen atoms join with one oxygen atom, forming a water molecule, H2O, a simple molecule, but with amazing properties. Water is a universal solvent, a liquid that expands when freezing, an almost unique property, a substance without which life, as we know it, is impossible. Or take glucose, C6H2O6, a simple sugar consisting of 24 atoms. This is the fuel of life, a molecule that stores the sun's energy, captured by plants in the process of photosynthesis, and releases it in your cells, allowing you to think, move, live. DNA, the code of life. At a scale of about 2 nanometers in width and micrometers in length, we encounter one of the most important molecules in the universe, deoxyribonucleic acid, or DNA. DNA is a double helix consisting of billions of atoms organized into an elegant structure. It contains instructions for creating and maintaining a living organism. The genetic code is written as a sequence of 4 chemical bases: adenine A, thymine T, guanine G, and cytosine C. Your genome, the complete set of genetic instructions, contains about 3 billion base pairs. If you imagine them as letters, your genetic code is a book of 3 billion letters. If you read 1 letter per second, it would take almost 100 years to read it from beginning to end. If you unwind all the DNA from one of your cells into a straight line, it would stretch approximately 2 meters. And if you connect the DNA from all your cells, about 37 trillion, you get a thread about 20 billion kilometers long. That's the distance from Earth to Pluto and back several times. But the most amazing thing about DNA is not its structure, but what it does. DNA contains instructions for creating proteins, molecular machines that perform practically all functions in your organism. About 20,000 genes encode hundreds of thousands of different proteins. These proteins build your body, digest food, protect against diseases, allow you to think and feel. Proteins, molecular machines. Proteins are the workhorses of the cell. They consist of long chains of amino acids folded into complex three-dimensional structures. There are 20 different amino acids, and their combinations create an endless variety of proteins. Hemoglobin carries oxygen in your blood. Antibodies protect you from infections. Enzymes catalyze chemical reactions, accelerating them by millions of times. actin and myosin contract, allowing your muscles to move. Each protein is a molecular machine created with nanometer precision to perform a specific task. Some proteins are incredibly complex. The ribosome, a molecular machine that reads RNA and synthesizes proteins, consists of more than 50 proteins and several RNA molecules containing millions of atoms. It works at a speed of about 20 amino acids per second, rarely making mistakes. Viruses, on the boundary of life. At a scale of 20 to 300 nanometers, are viruses, strange entities on the boundary between living and non-living. A virus is simply a set of genetic instructions, DNA or RNA, packaged in a protein shell. A virus has no metabolism. It cannot reproduce independently. Outside a host cell, a virus is an inert chemical object, no more alive than a salt crystal. But entering a cell, a virus comes alive. It hijacks the cellular machinery, forcing it to produce thousands of copies of the virus. A virus is a molecular pirate, a hijacker of cellular systems. Viruses have played a huge role in the evolution of life. About 8% of the human genome consists of sequences left by ancient viruses. Some of these viral genes now perform important functions, including the development of the placenta in mammals. Cell, the factory of life. At a scale of 10 to 100 micrometers, 10 meters, we reach the cell, the basic unit of life. A cell is a self-reproducing chemical factory of incredible complexity. A typical animal cell contains about 100 trillion atoms organized into millions of molecules working in perfect coordination. Imagine a city with a population of millions of inhabitants, where everyone knows their job and performs it in perfect harmony. That's what a cell is. The cell membrane, a thin double layer of lipids, separates the cell's internal environment from the external world. It's not just a barrier, but a complex system controlling what enters and exits the cell. Mitochondria, the cell's power stations, produce ADP, adenosine triphosphate, the universal energy currency of life. Each of your cells contains hundreds of mitochondria producing millions of ADP molecules per second. Interesting fact, mitochondria have their own DNA, distinct from nuclear DNA. This is because they were once independent bacteria that about 2 billion years ago entered into symbiosis with larger cells. Ribosomes, molecular machines synthesizing proteins according to instructions encoded in DNA. In each of your cells, millions of ribosomes work around the clock, producing thousands of proteins every second. The nucleus, the cell's command center, contains chromosomes with your DNA. Here genes are transcribed into RNA, which is then sent to the cytoplasm for protein production. The endoplasmic reticulum, a complex network of membranes, is involved in the production and transport of proteins and lipids. The Golgi apparatus, the sorting center, modifies, packages, and sends proteins to their destination. Lysosomes, cellular garbage disposals, break down waste and worn-out components. All of this works in perfect coordination. Thousands of chemical reactions occur every second. Signaling molecules transmit information. Molecular motors transport cargo along microtubules, cellular railways. The cell constantly builds new components, repairs damage, adapts to a changing environment. And all of this happens in a volume smaller than the period at the end of this sentence. Multicellular organisms. Cooperation leads to complexity. Single-celled organisms have existed for billions of years. But about 600 to 800 million years ago, something amazing happened. Cells began to unite into multicellular organisms. Multicellularity opened completely new evolutionary possibilities. Cells could specialize. Some became nerve cells, others muscle cells, still others skin cells. Division of labor led to an incredible increase in complexity. Your body contains about 37 trillion cells. That's approximately 5,000 cells for every person who has ever lived on Earth. These cells are organized into more than 200 different types: neurons, cardiomyocytes, osteoblasts, leukocytes, erythrocytes, and so on. Every second in your body, about 1 to 2 million cells die, and the same number are born. You're literally constantly renewing yourself. Most of your skin cells are replaced every 2 to 3 weeks. Red blood cells live about 120 days. Cells lining your stomach are replaced every 5 days. The ship of Theseus paradox applies to you. If all parts of ship are gradually replaced, does it remain the same ship? If almost all cells of your body are replaced every 7 to 10 years, do you remain the same person? Human scale. At a scale of 1 to 2 meters is the human. You, the being reading these words and trying to understand your place in the cosmos. The human is the most complex known structure in the universe. Yes, galaxies are enormous. Yes, black holes are incredibly massive. But nothing known to us can compare in level of organized complexity with the human body, and especially with the human brain. The human brain, the most complex structure. Your brain weighs about 1.4 kilograms, approximately 2% of body mass. But it consumes 20% of all the organism's energy. It's the most energy-intensive organ, and for good reason. The brain contains about 86 billion neurons, approximately as many as there are stars in our galaxy. But that's only the beginning. Each neuron is connected to thousands of other neurons through structures called synapses. The total number of synapses in your brain is about 100 to 500 trillion. The number of possible states of the human brain, determined by patterns of neuron activation, exceeds the number of atoms in the observable universe. Read, your brain is capable of a greater variety of states than there are atoms in the entire cosmos. Every second, billions of electrochemical reactions occur in your brain. Neurons exchange signals at speeds up to 120 meters per second. Information passes through complex networks, is processed in parallel by thousands of different pathways, is integrated into a unified, continuous experience of reality. And from all this complexity arises consciousness, perhaps the deepest mystery of science. What is consciousness? How do billions of individual neurons exchanging electrical impulses generate subjective experience? The sensation of the experience of the color red, the taste of chocolate, the feeling of love. Philosopher David Chalmers calls this the hard problem of consciousness. We can explain how the brain processes information, controls movements, forms memories. But we cannot explain why all this is accompanied by subjective experience. Why is there someone inside us? Some philosophers and scientists suppose that consciousness may be a fundamental property of the universe, as basic as mass or charge. Perhaps the simplest forms of consciousness or proto-consciousness are present even at the level of elementary particles, and human consciousness is simply an incredibly complex version of something universal. The human body, a symphony of systems. But the brain is only part of the incredible machine that is your body. The heart beats about 100,000 times a day, pumping 7,500 liters of blood through 96,000 kilometers of blood vessels. That's more than twice around the Earth at the equator. The lungs contain about 300 million alveoli, tiny air sacs where the exchange of oxygen and carbon dioxide occurs. The total surface area of the lungs is about 70 square meters, the size of a tennis court, packed into your chest cavity. The digestive system is a 9-meter tube from mouth to anus, containing an entire ecosystem of trillions of bacteria. In fact, there are approximately as many bacterial cells in your body as human cells. You're not an individual, but a walking ecosystem, a symbiosis of human and microbes. The immune system is an army of billions of cells patrolling your body, recognizing and destroying pathogens. It possesses an amazing ability to distinguish self from non-self, remember past infections, and create antibodies against practically any possible pathogen. The skeleton is not just a framework, but living tissue constantly renewing itself. Your bones are a mineral warehouse and a blood-forming factory. In bone marrow, about 2 million red blood cells are produced every second. Skin is the body's largest organ, weighing about 4 kilograms and covering an area of about 2 square meters. It protects you from infections, regulates temperature, synthesizes vitamin D, serves as a barrier between you and the hostile world. All these systems work in perfect coordination, controlled by a complex interaction of the nervous and endocrine systems. Hormones, neurotransmitters, enzymes, electrical impulses. All this creates an incredible symphony of physiology, allowing you to exist, move, think, feel. Human is process, not thing. Here's the key insight. You are not a static object. You are a process, a constantly flowing pattern of matter and energy. Every atom in your body was once part of something else. The carbon in your proteins was part of a plant you ate, which obtained it from the atmosphere. The oxygen you're breathing right now was produced by a tree on another continent. The hydrogen in the water molecules of your body has existed since the Big Bang, traveled through space for billions of years before becoming part of you. You are a temporary configuration of stardust. Atoms pass through you like water flows through a river. The river remains a river, although the water constantly changes. You remain yourself, although your atoms are constantly being replaced. Buddhists call this anatman, the absence of a permanent, unchanging self. Modern science confirms ancient wisdom. There is no static you. There is only a process, a pattern, a dance of matter and energy that for a time maintains its form before dissolving back into the universe. Philosophical digression. What does it mean to be human? Before leaving human scale and traveling further, let's think. What makes us special? We are the only known species capable of questioning our own existence. Animals live in the present. They react to stimuli, follow instincts, perhaps have primitive self-awareness. But only humans can reflect on the past, plan the distant future, create art, science, philosophy. Only humans can look at the night sky and wonder, what's there beyond the stars? Where do we come from? Where are we going? Are we alone in the universe? We create meanings in a meaningless universe. We write poetry, compose music, build cathedrals and spaceships. We discovered quantum mechanics and the theory of relativity. We split the atom and sent machines to the edge of the solar system. In just 10,000 years, a moment in cosmic time, we've traveled the path from hunter-gatherers to a civilization capable of changing the planet's climate and reaching other worlds. The paradox of humanity is that we're incredibly small and incredibly significant simultaneously. Physically, we're specks of dust in space, but we're the only known specks capable of understanding the cosmos, creating mathematics, describing its laws, building machines to explore it. Carl Sagan said, "We are a way for the cosmos to know itself." Biosphere, the thin film of life. Rising to kilometer scales, we begin to see the biosphere, the zone of life on Earth. The biosphere extends from the deepest ocean trench, the Mariana Trench, 11 kilometers below sea level, where bacteria and even multicellular organisms have been discovered, to the upper layers of the atmosphere, bacterial spores found at altitudes of 40 kilometers. This is only about 50 kilometers, thinner than an orange peel in proportion to its size. All known life in the universe exists in this incredibly thin film on the surface of one rocky planet. Life on Earth is incredibly diverse. Estimates vary, but possibly there are from 5 to 10 million species of eukaryotes, organisms with a nucleus and cells, not counting millions or billions of species of bacteria and archaea. We've described and named only about 2 million species. We're still discovering our own planet. All this life is connected in a complex web of ecosystems. Plants produce oxygen that animals breathe. Animals exhale carbon dioxide that plants use. Fungi decompose dead matter, returning nutrients to the soil. Everything is connected to everything. The Gaia hypothesis, proposed by James Lovelock, asserts that the entire biosphere functions as a single self-organizing superorganism. Life doesn't just adapt to the environment, it actively regulates it, maintaining conditions favorable for life. Earth, the blue planet. Earth has a diameter of 12,742 kilometers and a mass of about 6 times 10 superscript 2 kilograms. From space, our planet looks like a perfect blue sphere with white swirls of clouds and brown patches of continents. The blue marble photograph, taken by the Apollo 17 crew in 1972, became one of the most recognizable images in history. Earth is the only planet in the solar system with liquid water on the surface. Water covers 71% of Earth's surface. Oceans contain 97% of all water on the planet, and the remaining 3% is fresh water, most of which is frozen in the ice caps of Antarctica and Greenland. Why is Earth so perfect for life? It's a combination of many factors. The right distance from the Sun, about 150 million kilometers in the so-called habitable zone or Goldilocks zone, where temperature allows water to exist in liquid state. The right mass, large enough to hold an atmosphere by gravity, but not so large that the atmosphere becomes too dense and toxic, as on Venus. Magnetic field, generated by Earth's liquid iron core, protects us from solar wind and cosmic rays, which would otherwise destroy the atmosphere and make the surface unsuitable for life. The Moon stabilizes Earth's axial tilt at 23.5 degrees, creating stable seasons. Without the Moon, Earth's axis would chaotically oscillate, creating extreme climate changes, possibly incompatible with complex life. Plate tectonics. The movement of continental plates regulates climate through the carbon cycle, creates landscape diversity, generates the magnetic field through convection in the mantle. All these factors had to come together. Change any of them, and Earth could have become a lifeless desert like Mars or a toxic hell like Venus. Earth's history: 4.5 billion years of evolution. Earth formed about 4.54 billion years ago from a protoplanetary disk around the young sun. The first billion years was a period of intense bombardment by asteroids and comets. Earth was a molten hell. About 4.5 billion years ago, a Mars-sized protoplanet that scientists named Theia crashed into the early Earth. This cataclysm ejected a huge amount of matter into orbit, from which the Moon formed. This collision also gave Earth its axial tilt. By 3.8 billion years ago, oceans already existed. And somewhere between 3.5 and 4 billion years ago, life appeared, perhaps in hot springs on the ocean floor or in shallow tidal pools. We don't know exactly how life arose, but we know it appeared surprisingly quickly after conditions became suitable. The next 2 billion years, life remained single-celled. Simple bacteria and archaea dominated, but they were slowly changing the planet. Cyanobacteria began producing oxygen through photosynthesis. Oxygen was toxic to most organisms of that time. The Great Oxidation Event occurred about 2.4 billion years ago, which caused a mass extinction of anaerobic organisms. But oxygen also opened new possibilities. It allowed aerobic respiration to develop, a much more efficient way of extracting energy from food. About 1.8 billion years ago, the first eukaryotes appeared, cells with a nucleus. About 600 to 800 million years ago, the first multicellular organisms arose. 540 million years ago, the Cambrian explosion, a sudden, in geological terms, diversification of life forms. In a relatively short period of 20 to 25 million years, almost all major groups of animals appeared. Life came ashore about 470 million years ago. First plants, then arthropods, then vertebrates. Dinosaurs dominated in the Mesozoic, 252 to 66 million years ago. Their era ended 66 million years ago when a 10-kilometer asteroid crashed into the Yucatan Peninsula, causing a mass extinction that destroyed 75% of all species. This extinction freed ecological niches for mammals. Primates appeared about 60 million years ago. The genus Homo arose about 2 to 3 million years ago. Homo sapiens, our species, appeared about 300,000 years ago in Africa. Just 10,000 years ago, 0.003% of Earth's history, humans invented agriculture and began building civilization. 200 years ago, less than 0.00004% of Earth's history, the Industrial Revolution began. If you compress all of Earth's history into 24 hours, life appears at 4 a.m. Multicellular organisms at 9 p.m. Dinosaurs rule from 11 p.m. to 11:40 p.m. Homo sapiens appears 1.4 seconds before midnight. All of recorded human history, the last 0.2 seconds. Moon, our cosmic companion, at a distance of 384,400 kilometers from Earth orbits the Moon, the only natural satellite of our planet. The Moon is an unusually large satellite for a planet the size of Earth. Its diameter is 3,474 kilometers, about a quarter of Earth's. The Earth-Moon system is sometimes considered a double planet. The Moon is gravitationally locked. It's always turned toward Earth with one side. The far side of the Moon was first seen by humans only in 1959, when the Soviet probe Luna 3 flew around it. On July 20th, 1969, Neil Armstrong became the first human to set foot on the surface of another world. Between 1969 and 1972, 12 people walked on the Moon. Since then, no human has traveled farther from Earth than low Earth orbit. A regrettable fact showing that progress isn't always linear. The Moon is slowly moving away from Earth, approximately 3.8 centimeters per year. The gravitational interaction of Earth and Moon slows Earth's rotation, lengthening our days by approximately 2 milliseconds per century. Billions of years ago, a day on Earth lasted only about 6 hours, and the Moon was much closer. Artificial satellites, the new ecosphere. Thousands of artificial satellites orbit Earth, from the size of a refrigerator to the size of a bus. They provide GPS navigation, telecommunications, weather monitoring, military reconnaissance, scientific research. The International Space Station, ISS, is the largest artificial structure in orbit, the size of a football field. Humans have been continuously living in space since 2000, already more than 24 years of human presence beyond Earth. Unfortunately, the space around Earth is also becoming a garbage dump. Kessler syndrome is a hypothetical scenario in which the density of objects in low Earth orbit becomes so high that collisions generate a cascade of further collisions, making orbit unsuitable for use. This is a real threat to the future of astronautics. Leaving Earth, we enter scales where kilometers become inconvenient. Astronomers use the astronomical unit, EU, the average distance from Earth to the Sun, about 150 million kilometers. At this scale, space becomes truly empty. If you shrink the solar system so that Earth was the size of a pea, the Sun would be a basketball 23 meters from it. Jupiter would be an apple at 122 meters. Pluto would be a pinhead at 920 meters. The nearest star, Proxima Centauri, would be at a distance of 6,200 kilometers. Space is mostly emptiness. Sun, our star. At the center of our system is the Sun, a star of spectral class G2V, an ordinary yellow dwarf of middle age. The Sun's diameter is 1.4 million kilometers, which is 109 times larger than Earth. 1.3 million planets the size of Earth could fit inside the Sun. But despite its size, the Sun is quite rarefied. Its average density is only 1.4 G/cm superscript 3, slightly more than water. The Sun's mass is 2 times 10 superscript 3 kilograms, which constitutes 99.86% of all the mass of the solar system. All planets, asteroids, comets, dust, all this is only 0.14% of the total mass. In the Sun's core, at a temperature of 15 million degrees Celsius and pressure of 250 billion atmospheres, thermonuclear fusion occurs. Every second, 600 million tons of hydrogen fuse into 596 million tons of helium. The missing 4 million tons are converted into pure energy according to Einstein's formula equals mc squared. This energy, 3.8 times 10 superscript 2 watts, slowly makes its way through the dense plasma of the Sun. It can take a photon from 10,000 to 170,000 years to travel from the core to the surface. But after leaving the Sun, light reaches Earth in just 8 minutes 20 seconds. Every second, Earth receives about 174 petawatts, 1.74 times 10 superscript 1 watts of solar energy. In 1 hour, Earth receives more energy from the Sun than all humanity consumes in a year. If we could efficiently collect solar energy, humanity's energy problems would be solved. The Sun has existed for about 4.6 billion years, approximately half of its life cycle. In 5 billion years, when the hydrogen in the core runs out, the sun will begin expanding into a red giant, possibly swallowing Mercury, Venus, and possibly Earth. Then it will shed its outer layers, leaving a white dwarf, a hot, dense core the size of Earth, which will slowly cool for trillions of years. Inner planets, rocky worlds. Mercury, the closest planet to the Sun, is at a distance of 39 cents. It's a small world with a diameter of 4,879 kilometers, covered with craters resembling the Moon. It has practically no atmosphere. Daytime temperature reaches 430 degrees Celsius. Nighttime drops to minus 180 degrees Celsius, the largest temperature range in the solar system. Venus, 72 cents, diameter 12,104 kilometers, Earth's twin planet in size, but hellish in conditions. A dense carbon dioxide atmosphere creates the most powerful greenhouse effect, heating the surface to 462 degrees Celsius, enough to melt lead. Atmospheric pressure is 92 times higher than Earth's. Sulfuric clouds rain sulfuric acid. Venus is a warning about what can happen when the greenhouse effect goes out of control. Earth, $1 12,742 kilometers, the only known world with life. Mars, $1 52 cents, 6,779 kilometers, the red planet, named after the Roman god of war due to its blood-red color caused by iron oxide, rust, on the surface. Mars was once a warm and wet world with rivers, lakes, possibly oceans. But about 3.5 billion years ago, Mars lost its magnetic field and most of its atmosphere. Today, it's a cold desert with an atmosphere 100 times more rarefied than Earth's. Robot explorers have been studying Mars since the 1960s. The Curiosity and Perseverance rovers are searching for signs of ancient life. Mars is the most likely target for a future manned mission. Elon Musk dreams of making humanity an interplanetary species, starting with the colonization of Mars. Asteroid belt. Between Mars and Jupiter, at a distance of 2.2 to 3.2 AU, is the asteroid belt, a region containing millions of rocky and metallic bodies. The largest object in the belt is Ceres, a dwarf planet with a diameter of 940 kilometers. In total, the belt may contain 1 to 2 million asteroids with diameters greater than 1 kilometer and millions of smaller ones. Contrary to Hollywood representations, the asteroid belt isn't densely packed with rocks. The average distance between asteroids is hundreds of thousands of kilometers. A spacecraft could fly through the belt without even seeing a single asteroid. Jupiter, king of the planets. At a distance of $5.20 reigns Jupiter, a giant gas ball with a diameter of 139,820 kilometers, 11 times larger than Earth. Jupiter is so massive, 318 times heavier than Earth, that all the other planets of the solar system could fit inside it. It contains about 70% of all planetary mass in the system. Jupiter has no solid surface. It's simply layers of gas becoming denser with depth. The outer atmosphere consists mainly of hydrogen and helium. Deeper, gases turn into liquid. Even deeper, hydrogen is compressed so strongly that it becomes metallic, a state of matter that doesn't exist on Earth. The Great Red Spot, a giant anticyclone in Jupiter's atmosphere, is larger than the entire Earth. This storm has been raging for at least 400 years, since humans first saw it through telescopes. Jupiter has 79 known moons. The four largest, Io, Europa, Ganymede, and Callisto, are called Galilean in honor of Galileo Galilei, who discovered them in 1610. This discovery became one of the first proofs that not everything revolves around Earth. Europa is one of the most intriguing worlds in the solar system. Under an ice crust 10 to 30 kilometers thick lies a global ocean of liquid water up to 100 kilometers deep, more water than in all of Earth's oceans combined. Jupiter's tidal forces heat Europa's interior, possibly creating hydrothermal vents on the ocean floor. Life on Earth thrives at such vents. Could life exist in Europa's ocean? NASA is planning the Europa Clipper mission to investigate this question. Jupiter plays an important role in protecting the inner solar system. Its powerful gravity deflects or captures many comets and asteroids that would otherwise bombard Earth. Without Jupiter, life on Earth might not have developed. Saturn, ring beauty. At a distance of $9.50 is Saturn, diameter 116,460 kilometers. Perhaps the most beautiful planet in the solar system, thanks to its magnificent rings. Saturn's rings extend 280,000 kilometers from the planet, but are surprisingly thin, only 10 meters to 1 kilometer in thickness. They consist of billions of particles of ice and rock ranging in size from microns to several meters. The origin of the rings remains a mystery. Perhaps they formed from the remains of a destroyed moon or comet, or their primordial material left over from Saturn's formation. The rings may be relatively young, only 100 to 200 million years. Saturn has 82 known moons. The largest is Titan, the only moon in the solar system with a dense atmosphere. Titan is larger than Mercury. Its atmosphere is 1.5 times denser than Earth's, consisting mainly of nitrogen with an admixture of methane. On Titan, methane rains fall, methane rivers flow, there are methane lakes and seas. It's the only world besides Earth where stable liquids on the surface have been confirmed. The temperature there is minus 179 degrees Celsius, but complex organic chemistry occurs constantly. Some scientists suppose that life based not on water, but on liquid methane could exist on Titan. Uranus and Neptune, ice giants. Uranus, $19.20, diameter 50,724 kilometers, and Neptune, $30, 49,244 kilometers, are the most distant planets in the solar system, cold worlds at the edge of the system. Uranus is unique in that its axis of rotation is tilted at 98 degrees. It essentially rotates lying on its side. Each pole alternately receives 42 years of continuous sunlight, then 42 years of darkness. Neptune is the windiest planet in the solar system. Winds in its atmosphere reach 2,100 kilometers per hour, faster than the speed of sound. Why such a distant and cold planet possesses such turbulent weather remains a mystery. Kuiper Belt and dwarf planets. Beyond Neptune's orbit, beginning at approximately $30 and extending to $50, is the Kuiper Belt, a region filled with icy bodies left over from the formation of the solar system. Pluto, discovered in 1930 and considered the ninth planet until 2006, is now classified as a dwarf planet. It's smaller than the Moon, with a diameter of only 2,377 kilometers. In 2015, the New Horizons probe flew past Pluto, revealing an unexpectedly geologically active world with nitrogen glaciers, mountains of water ice, and a possible subsurface ocean. Oort cloud, the boundary of the system. far beyond the Kuiper Belt at a distance from 2,000 to 100,000 Australian dollars, almost 2 light years, extends the Oort cloud, a giant spherical shell of trillions of icy bodies surrounding the solar system. The Oort cloud has never been directly observed. It's too far away, and the objects in it are too small and dim. But its existence is predicted based on the orbits of long-period comets that arrive from this region. When the gravitational influence of a passing star or galactic tidal effect disturbs an object in the Oort cloud, it could begin a long journey to the inner solar system, becoming a comet. The Oort cloud is the true boundary of the Sun's gravitational influence. Beyond its limits begins interstellar space. Voyagers, ambassadors of humanity. In 1977, NASA launched 2 space probes, Voyager 1 and Voyager 2, to explore the outer solar system. After epic missions to Jupiter, Saturn, Uranus, and Neptune, both Voyagers continued their journey toward interstellar space. In August 2012, Voyager 1 crossed the heliopause, the boundary where solar wind yields to the interstellar medium, becoming the first human-made object to leave the solar system. Currently, Voyager 1 is at a distance of more than 24 billion kilometers from Earth, 160 Australian dollars. A radio signal from it takes 22 hours to reach Earth. The probe is moving at a speed of 17 kilometers per second, but even at this speed, it would take 40,000 years to reach the nearest star. Aboard each Voyager is a golden record, a message from humanity to potential extraterrestrial civilizations. It contains sounds and images of Earth, greetings in 55 languages, music of various cultures and epochs, sounds of nature, diagrams showing the position of the Sun relative to pulsars. Astronomer Carl Sagan, who headed the team creating the record, wrote, "The launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Even when the Sun becomes a red giant and swallows Earth, the Voyagers will continue their eternal journey through the galaxy, carrying a message from a civilization that will no longer exist. Light year, a new unit of measurement. Leaving the solar system, we enter scales where even astronomical units become inconvenient. Now we measure distances in light years, the distance that light travels in a year, moving at a speed of 299,792 kilometers per second. 1 light year equals approximately 9.5 trillion kilometers, or 63,241 astronomical units. Light from the Sun reaches Earth in 8 minutes. Light from the nearest star travels more than 4 years. Light from the center of our galaxy travels 26,000 years. When you look at the stars, you're looking into the past. Nearest stars. The nearest star system to us, Alpha Centauri, is at a distance of 4.37 light years, 41.3 trillion kilometers. It's a triple system consisting of 2 Sun-like stars, Alpha Centauri A and B, orbiting a common center of mass, and a small red dwarf Proxima Centauri, located slightly closer to us, 4.24 light years. In 2016, astronomers discovered an Earth-type planet orbiting in the habitable zone of Proxima Centauri. Proxima Centauri b is only 4.24 light years from us, the closest known exoplanet. Could there be life there? We don't know. Proxima Centauri is a red dwarf known for its powerful flares that could sterilize the planet's surface. But perhaps life found a way to survive. With current technologies, a journey to Proxima Centauri would take tens of thousands of years. Even moving at Voyager 1's speed, 17 kilometers per second, It would take 73,000 years. The Breakthrough Starshot project proposes using a laser sail to accelerate tiny probes to 20% of the speed of light, which would allow reaching Alpha Centauri in 20 years. But this is still a conceptual idea. Solar neighborhood. Within a radius of 15 light years from the Sun are about 60 star systems containing approximately 80 stars. Many stars are in binary or triple systems. Most of them are red dwarfs, dim stars with masses of 0.1 to 0.6 solar masses. Red dwarfs constitute about 75% of all stars in the galaxy, but they're so dim that not one of them can be seen with the naked eye, even the nearest Proxima Centauri. There are also white dwarfs, cooled remnants of stars that have exhausted their thermonuclear fuel. Sirius B, the companion of Sirius, the brightest star in the night sky, is a white dwarf about the size of Earth, but with a mass around that of the Sun. White dwarf matter is so dense that a teaspoon would weigh tons. There are brown dwarfs, failed stars, insufficiently massive, less than 0.08 solar mass, to ignite thermonuclear fusion of hydrogen. They exist in an intermediate state between planets and stars. Interstellar medium. The space between stars is not absolute void. The interstellar medium contains rarefied gas, mainly hydrogen and helium, and cosmic dust. The density of the interstellar medium is incredibly low, on average about 1 atom per cubic centimeter. For comparison, air at sea level contains about 10 superscript 1 molecules per cubic centimeter. The best vacuum we can create on Earth is still 1,000,000 times denser than the interstellar medium. Despite such rarefaction, the interstellar medium plays a critical role in galaxy evolution. Stars are born from interstellar gas and dust gathering into clouds under gravity's action. When massive stars die in supernovae, they eject material enriched with heavy elements back into the interstellar medium, from which new generations of stars form. Nebulae, stellar nurseries. Regions where interstellar gas is especially dense, up to 10 atoms per cubic centimeter, are called nebulae. The Orion Nebula is the nearest region of active star formation to us, located just 1,344 light-years away. It's visible to the naked eye as a fuzzy patch in Orion's sword. Inside this nebula, in dense clouds of gas and dust, thousands of new stars are being born right now. The Hubble Space Telescope has taken stunning images of the Orion Nebula, showing protoplanetary disks around young stars, places where new planetary systems are forming. Each of these stars may have its own planets, possibly its own life. Planetary nebulae. These have nothing to do with planets, are shells of gas shed by dying stars. When a sun-like star exhausts its fuel, it swells into a red giant, then sheds its outer layers, creating a glowing cloud of gas around a hot core. The Ring Nebula, Cat's Eye Nebula, Butterfly Nebula, all these are beautiful monuments to dead stars. Supernova remnants are expanding clouds of debris from exploded massive stars. The Crab Nebula is a supernova remnant observed by Chinese astronomers in 1054. At its center is a pulsar, a rapidly rotating neutron star emitting radio pulses 30 times per second. Galaxy structure. Rising to a scale of thousands of light years, we begin to see the structure of our galaxy, the Milky Way. The Milky Way is a barred spiral galaxy with a diameter of about 100,000 to 120,000 light years and a thickness of about 1,000 light years in the disk, not counting the halo. It contains 200 to 400 billion stars, The exact number is unknown and has a mass of about 1.5 trillion solar masses, including dark matter. The galaxy has several main structures. The bulge, central thickening, a dense spheroidal region at the center containing old stars and a supermassive black hole. The disk, a flat region where most stars are located, including our Sun. The disk contains spiral arms, regions of increased density of stars and gas where star formation is active. Spiral arms. The Milky Way has 4 main arms: Perseus, Sagittarius Carina, Scutum Centaurus, and the outer arm. The Sun is located in a small branch called the Orion Arm or Orion Spur between the Perseus and Sagittarius Carina arms. The halo, a spherical region surrounding the disk containing old stars, globular clusters, and a large amount of dark matter. The Sun's position. The Sun is at a distance of approximately 26,000 light-years from the galactic center, approximately 2/3 of the way from the center to the edge of the disk. We orbit the center of the galaxy at a speed of about 220 kilometers per second. One complete orbit, a galactic year, takes approximately 225 to 250 million Earth years. Since the formation of the solar system, 4.6 billion years ago, we've made only about 20 orbits around the galaxy. When dinosaurs ruled Earth, we were on the other side of the galaxy. Each time we pass through a spiral arm, the density of stars around us increases, possibly affecting the frequency of comets passing through the Oort cloud and, consequently, the frequency of mass extinctions on Earth. This is a hypothetical theory, but it shows that even galactic processes can affect life on Earth. Galactic center, supermassive black hole. At the very center of the Milky Way, in the direction of the constellation Sagittarius, is Sagittarius, a supermassive black hole with a mass of about 4 million solar masses. This black hole has a Schwarzschild radius, event horizon, of about 12 million kilometers, approximately 17 solar radii. Everything that crosses this horizon is forever lost to the external universe. We cannot see the black hole itself, but we can observe its gravitational influence on surrounding stars. Astronomers have tracked the orbits of stars around Sagittarius A for decades. One star, S2, has an orbital period of only 16 years and passes just 17 light hours from the black hole, moving at speeds up to 7,650 kilometers per second, 2.55% of the speed of light. In 2019, the Event Horizon Telescope project obtained the first image of a black hole shadow, not Sagittarius A-, but a more massive black hole in the center of galaxy M87. In 2022, a photograph of Sagittarius A-'s shadow was published, a ring of light around a dark silhouette where gravity is so strong it bends light around itself. Practically every large galaxy has a supermassive black hole at its center. Somehow, these monstrous objects play a key role in the formation and evolution of galaxies, although the details of this process are still being studied. Globular clusters. Around the galaxy, in the halo, about 150 globular clusters orbit, dense spherical groups, each containing from tens of thousands to millions of stars. Globular clusters are some of the oldest objects in the galaxy, their age reaching 12 to 13 billion years, almost the age of the universe. The stars in them are old, red, poor in heavy elements. They formed when the galaxy was young. In the center of a globular cluster, stars are packed so densely that the distance between neighboring stars can be just fractions of a light year. If we lived on a planet in such a cluster, The night sky would glow with thousands of stars brighter than Venus. Exoplanets, worlds around other stars. Until 1992, we didn't know for certain whether planets existed around other stars. Today, we've confirmed the existence of more than 5,500 exoplanets in more than 4,000 planetary systems. These planets are incredibly diverse. Hot Jupiters, giant gas planets orbiting very close to their stars, with surface temperatures above 1,000 degrees Celsius. Super-Earths, rocky planets with masses several times that of Earth. Neptunes, ice giants of various sizes. Planets in the habitable zone, worlds where temperature allows liquid water to exist on the surface. The Kepler mission showed that planets are extremely common. Practically every star has at least one planet. Estimates suggest that there may be 40 billion Earth-type planets in the habitable zones of their stars in the Milky Way. 40 billion possible worlds where life could exist. Only in our galaxy. Fermi paradox. Where is everyone? This brings us to the famous Fermi paradox. If the universe is so vast and old, and planets are so common, where are all the aliens? Physicist Enrico Fermi asked this question in 1950. The Milky Way is 13.6 billion years old. Even with slow interstellar travel, an advanced civilization could colonize the entire galaxy in 50 to 100 million years, a moment in cosmic scales. Why don't we see signs of such civilizations? Many explanations have been proposed. We're alone. Life, or intelligent life, is exceptionally rare. The Great Filter. There exists a barrier that civilizations rarely overcome. Perhaps it's behind us. The emergence of life is extremely unlikely. Or ahead of us, advanced civilizations self-destruct. They exist, but are silent. Civilizations avoid contact for unknown reasons. We're looking wrong. Their technologies are so advanced that we cannot recognize their signals or artifacts. Zoo or quarantine. Advanced civilizations intentionally avoid contact with us. They're too far away. Space is so vast that even with many civilizations, the distances between them are insurmountable. Perhaps we'll get an answer in the coming decades when new telescopes begin analyzing the atmospheres of exoplanets in search of biosignatures, signs of life, or when radio telescopes hear a signal from deep space. Or perhaps we really are alone, and this makes us incredibly precious and fragile, the only witnesses to the beauty of the cosmos.